In this video, we're going to look at a graphical method of calculating the magnitude of transfer functions that sheds some light onto how filters work. Filter design can be a little opaque because the circuit theory requires calculating the values of loaded components that give rise to weird polynomials in the transfer function, but I find this graphical interpretation makes filters simpler to understand. The graphical method for calculating filter behavior has its roots in pole zero plots, so we're starting to understand this method by drawing a pole zero plot for this transfer function. I've taken the liberty of doing the quadratic equation for you on this first line, which reveals that we have poles at -1 minus j and -1 plus j, and I plotted those on the left. As a note, this is an example of a second order filter because there are two poles in the pole zero plot. We're only looking at h of s, not the magnitude of h of s squared, so we can't say for sure what fn is yet, but it's probably also quadratic. If we want to find the value of this transfer function at a point j omega, then we can just substitute j omega for s in our transfer function. This is equivalent to evaluating the transfer function at some point on the imaginary axis, because j omega is just a locus of points in the s-plane. That's cool enough that it bears repeating. The frequency response function for this transfer function is just the values along the imaginary axis, and we can find the frequency response function by evaluating the transfer function at every point on the imaginary axis. We can group like terms in the denominator of this expression, which starts to have a geometric interpretation. Each of these regrouped poles specifies a vector that points from a pole to the point j omega. For instance, the bottom pole is a distance 1 from the j omega point in the real direction, and a distance 1 plus omega from the pole in the imaginary direction. And that's captured by the second pole in our rightmost expression, which has a real value of 1 and an imaginary value of omega plus 1. We can take the magnitude of this expression, and in doing so we find that the denominator of this magnitude is the product of the lengths of the vectors from the poles to j omega. And that generalizes to any transfer function. The magnitude at a point on the s-plane, which I've labeled as j omega in our case, is the product of the lengths of the vectors that point from zeros to the point in question, divided by the product of the lengths of vectors pointing from poles to the point in question. So we can understand the behavior of our magnitude just by looking at the lengths of a bunch of vectors on the x-plane. We're going to apply that result to filters on the next slide, but I need to put in a sidebar about calculating phase graphically. There's a similar graphical technique for finding phase, where the phase of the transfer function is the sum of angles from zeros to the point in question, minus the sum of angles from poles to the point in question. That's a cool thing to remember, and it explains the baffling behavior of right half-plane zeros. In particular, right half-plane zeros contribute positive magnitude and negative phase to Bode plots, which I found super weird, and is very notable because it makes right half-plane zeros very bad for stability and feedback. You can see that behavior on this plot, because increasing omega will make the angle from the right half-plane pole smaller, shrinking the total phase of the transfer function. We can apply this graphical technique to understand how filters work. I've copied over the second order filter from the previous page and drawn a point omega in between the two poles. When I look at a different input frequency between the poles, we can see that the distance to one pole gets larger while the distance to the other pole gets shorter. That results in the overall transfer function staying flat. However, if I look at a value of j omega outside of the two poles, we find that both of the vectors to the poles are getting longer as omega increases. That means the value of the transfer function will start falling off quickly. And if I wanted to take advantage of that behavior, I could add a lot more poles at about the same distance from the origin. In this example of a fifth order filter, 5 poles have vectors that cancel out for omega points inside of a circle in the s-plane. But if the j omega point moves outside the circle, we'd also have 5 vectors getting longer and decreasing the transfer function. This change, where we add more poles to cause transfer functions to fall off more quickly, corresponds to increasing the order of the filter, and I've included the fn polynomials for these filters to show that. The second order filter uses the f2 polynomial, while the fifth order filter uses the f5 polynomial. This is a low-pass filter, which we've seen because the transfer function gets small when omega gets big. We'd have to move poles and zeros around in a dramatic way to make a high-pass filter, and in fact we usually do that by inverting omega and omega p in the prototype function, which is a crazy nonlinear transform. We'd need a different dramatic change for a bandpass or a bandstop filter, because either of those would require twice as many poles. And on the last slide, we saw how changing the filter order changed the behavior of filters. We can also change the behavior of filters by changing the location of poles. In the filter on the right, the poles are located on an ellipse instead of a circle, which will result in the length of the vectors to the omega point canceling imperfectly in the passband. But it also means the vectors get longer, faster outside of the passband, so we've traded some passband ripple for a faster roll-off in this arrangement of poles, even for filters with the same order. Positioning poles in this way required us to change the prototype polynomial to something called an nth-order Chebyshev polynomial, which we'll talk about more soon. So in summary, frequency responses can be calculated graphically as a product of magnitudes of distance from poles to points j omega on the imaginary axis. Filters have many poles at similar frequencies to achieve quick roll-off, and the arrangement of these poles is determined by the filter prototype polynomial.